My name is Stéphanie Guinehue, so I work at Mercator Ocean on service evolution activities, and this session is dedicated to the presentation of the service evolution R&D activities at Mercator Ocean, and we will highlight also some Horizon Europe projects. So at Mercator Ocean, I work on these activities together with Pierre-Yves, but also Angélique. She has moved to a new position, but we are still interacting together. So as we all know, Copernicus Marine is a continuously evolving service. In Copernicus 2, as we have seen yesterday, we will have regular incremental improvements to the current offer, as well as a series of major evolutions targeting the coastal zone, the Arctic Ocean, the marine biology, ocean climate, and digital services. And as Copernicus 2 has already started, we have already started to implement some of those evolutions through dedicated Horizon Europe projects, such as Focus, who will be presented later during the day for the coastal zone, such as Necton for the marine biology, but also we have Assiberg for the Arctic, as well as new high-resolution product at Pan-Arctic scale since last November. For the ocean climate, we are working on long reanalysis, but as well as through the new CCLIM and MOHAI projects. And for digital services, as we have seen this morning, we have the EDITO landscape. Service evolution principles. So the evolution is driven by user and policy needs. So I don't know if you had a chance to go and see Valentina yesterday. She has a poster on user requirements. It's still available in the corridor. And the service is also science-driven, so that scientific and technical advances are fully taken into account. And for those two activities, we benefit from guidance from two advisory groups, the QUAG on one side, the Champion User Advisory Group, and the STAC, the Scientific and Technical Advisory Committee on the other side. So to best organize this service evolution strategy, we have constructed together with the STAC, so our Scientific and Technical Advisory Committee, an R&D priority document where you can find priority topics covering 8 R&D overarching areas. So considering the next generation of integrated ocean forecasting systems, high-resolution monitoring and forecasting of the blue ocean, the Arctic Ocean, including sea ice analysis, modeling and forecasting, AI, big data and advanced data products, ocean climate products, indicators and projections, observations, inputs, and sensitivity studies, as well as biogeochemistry and the marine biology and the marine coastal environment. So this priority document is available on the Copernicus Marine website, and it's regularly updated, usually once a year. Also, to best organize the service, we have defined what we call streams. For the short term, what we call the tier 1, the mid-term, the tier 2, and the long-term R&D supporting the future evolution of the service. And of course, the overall objective is to integrate the developments in the operational systems. So I'm now going to describe each of them quite briefly. Starting with the tier 1, which correspond to the short-term evolutions. Those are addressed within the Copernicus Marine through the production centers, so mostly the people in this room, and resulting in regular update of the catalog. And as we have seen also yesterday, it's done through a series of formal reviews, starting with the specification, then going to the design, acceptance, before the entry into service. Then we have what we call the tier 2 for the mid-term evolutions. Those are addressed within Copernicus Marine, both through the production centers, but also open R&D service evolution calls, so dedicated calls. And those calls usually target topics defined in the Copernicus Marine Service Evolution Strategy R&D priority document. The objective of these R&D projects, which run usually during 2 years, is to obtain significant results during those 2 years, and then have the potential of concretely improving the operational service the following years. And to do that, a strong coordination is needed between these service evolution projects and the production centers, the TAC and MFCs, to foster the uptake of the results from those projects. And this is also why we are all together today, the production centers and some of the service evolution project leaders. During Copernicus 2, we had a first call in 2022, and we selected 14 projects which run from July 2022 to August 2024. You can find the summaries and the main outcomes of those projects on the Copernicus Marine website. And we have seen also yesterday that some of the uptake of the result from those projects is already happening in some TAC and MFCs. So we had projects dealing with new improved products, such as high-resolution, multi-resolution coastal ocean color products, merging information from Sentinel-2 and Sentinel-3. It was called Multi-Res. Then we had this OCIROC project, providing a particulate and dissolved organic carbon surface product, both for the coastal and the global ocean. The GLOPHY-TS project for long-time series of phytoplankton functional taps. And all three are planned to be integrated in the OCTAC evolutions. Then we had a project called SODA for the detection of sargassum algae. We had a project called OneBore for the ocean mass from GRACE, providing as well as freshwater fluxes estimation. And then 2 projects dealing with the next generation of sea level products, including the SWOT satellite with slicing and 4D Barnet. And we had a last project called ADEOS, which computed surface current from AIS data. Then we had some projects dealing with the upgrading, preparation of the next generation of operational systems. We had 2 projects dealing with advanced data assimilation methodologies, including ensemble-based and multi-grid with ODESA and Multicast. The COSI project for the calibration of sea ice forecasts, and some of this uptake is already planned in the ArcMFC. And then 3 projects targeting the coastal zone, monitoring, including a river-ocean interface with Estuario, wave modeling with Kelani, and coastal risk with risk assessment with coastal risk. And we have heard also from the Med and Black Sea MFC yesterday that they will implement the estuary box model, which has been partly developed during Estuario. Then during Copernicus 2, we had a second call beginning of last year, and we selected 12 projects which run from September 2024 until October 2026. And you can find the summary of those projects on the Copernicus Marine website, and each of them will be presented during this session. So I'm not going to detail them now. Then we have, first, considering the monitoring of those 12 projects, and fostering the uptake of the result of those projects by the TAC and MFC. So we are organizing a first meeting today, and we aim at organizing a second rendezvous closer to the end of those projects, and most probably in June 2026, together with a Copernicus Marine General Assembly. And as last time, you'll be provided with more information, the midterm report, and then the final report. The first one in October this year, and the second one at the end of the project. Then if I go to the Tier 3 activities, which correspond to the long-term evolution. Those are required to prepare major evolution, as the one I've listed previously. They are addressed externally with strong links with Horizon Europe projects, dedicated Horizon Copernicus Marine Evolution goals, ESA EUMETSAT national projects. And again, they require high level of coordination to prepare and ensure an efficient uptake. And today we will have two dedicated presentations, one for the coastal ocean with the FOCUS project, and one for the marine biology with the NECTON project. And here I listed additional projects, but in fact there are many more. And there will be, just to mention, there will be a specific call open through the Horizon Europe project targeting Copernicus Marine Evolution and specifically assimilation methods that should be open in the coming weeks. So Copernicus Marine is a continuously evolving product offer to remain an operational state-of-the-art European marine service for physics, sea ice, biogeochemistry, and low trophic level, to remain a marine reference worldwide by creating more marine value to foster further the service uptake. It's a user and policy needs as well as scientific and technological driven service. We will ensure the continuity of the service with incremental evolution. We will embrace new capabilities of digital services in synergy with the digital twin ocean development. And we are preparing the implementation of the next generation of ocean and sea ice monitoring and forecasting systems and new services for coastal and biology. So all this activity is supported by the different tiers, so the short-term, mid-term, and long-term R&D activities, and the different actors who contribute to them. So quickly, the agenda of today. So we will have 3 sessions, each of them targeted the presentation of 4 service evolution projects, followed by a short Q&A session. And at the end of the day, we will have the presentation of 2 Horizon Europe projects. And then, time permitting, we will have a small exchange all together to get your view if you think that we can improve this process. So I will now go to the first session, which targets new, improved, observation-based products. And I invite the first speaker, who is Vidar, to come to present his project. So you have the usual one, but you have a remote as well.
Thank you. My name is Vidar Lien. I'm from the Institute of Marine Research in Norway. And this is a nice picture of a younger me. I will talk about a project AIQC, where we aim to use enhance the real-time quality control by using AI or machine learning. Yeah, so we are developing machine learning-based methods for quality control of CTD data or profile data. We have a core team at IMR in Norway who is working on this, and you see a list of names. And it's first and foremost Asuka Yamakawa and Takaya Saito, who are the real workers in the project. I have more of an administrative role, and we have some other collaborators as well. We also have a couple of team partners, which are also our partners in the Institute TAC. That's Johanna Linders at SMHI and Athanasia Papapostoulou at HCMR in Greece. We also have a collaboration partner, so we are in contact with people at Alfred Wegener Institute, who has also been going in this direction. To exchange experiences and so on, and also IQOD. We are in contact with them. And we are also leveraging resources from AI for EOSC. So what we take aim at now is first and foremost temperature and salinity, and we also aim at oxygen and chlorophyll. But I would frankly say that that remains to be seen if that's doable, at least with the kind of methods and tools that we will apply. So because this, of course, is dependent on the availability of observations and the density of observations to train these kind of models. So if the data sources are not sufficient, then nothing useful will come out of it. So that remains to be seen. But this is our aim, at least. The main motivation, I would say, is twofold. We want to improve the automatic QC because the automatic or the near real-time data, where you only have time for automatic quality control, they go straight into the forecasting models. So if we can improve the quality of this near real-time quality control, then we will, in the second term, also improve the forecasts. So that's one main motivation. It's also a motivation that this will create a more cost-efficient system for quality control, thereby reducing the need for human workload in the delayed mode quality control. Not delete it, but reduce it. And this is illustrated here at the bottom, that we want to narrow the gap between the near real-time quality control and the delayed mode quality control as it is now, which, as I said, will then again improve the quality of the forecasts. And also, by applying these kind of methods, we can get a reliability information about quality flags, which will then help the manual QC afterwards, making that more efficient and reliable as well. So these are the main motivations for doing this. Just a short recap about the data flow in the Copernicus Marine Service in Situtak and where this project comes in. So we, or not we, but the providers are at sea doing measurements which are sent by satellite to land, and then in the upper area here, I can try to use a pointer. Upper area, you have automatic quality control, and then you get the near real-time product, right, which is what is going into the forecasts. And then in the middle, we have shown here, you have some manual QC, but that only comes afterwards. And that goes into what is then the delayed mode in situ product. So what this project here, at least in my sort of naive intuition, will help us with is to take some of the knowledge that sits in that guy in the middle there, in the manual QC, and put that into the automatic QC, and thereby improving the quality control on the daily basis. So that is where we come in this in these data flows. We have a quite ambitious work plan. We just started this autumn, so I've ticked the first task. I would say that is done, more or less. So the first work package, we are on data requirements, where we will identify the needed variables and data labeling. And we also need to identify the reliable data sources, verify the accuracy and consistency before we start using them to train the models. And we also need to do some, or are doing, ongoing exploratory data analysis to determine characteristics and patterns and so on in the data. When that is done, we will move on to the model development in work package 2, which is preparation of the training data set. And then we will identify models, which models are most suitable, because there are several ways to do this. And that will be done through testing and tuning of different approaches. And this is definitely where we also want to collaborate with others to gain experience and so on. And then we will do the training and validation and testing through iterative optimization processes. And when that is done, we will move on to, in work package 3, onto pilot and deployment. Then we will deploy this system in the operational data pipelines at IMR, and test it in an operational environment. And when that is successfully done, hopefully, we will package the machine learning model into a format suitable for deployment elsewhere as well. And in this also we need to implement monitoring infrastructure to track the performance and see if the model is drifting and maybe need some retraining and so on. And then we have in work package 4, we have promised to then provide the implementation plan where we make the results public, disseminate them, and also make the code available. And we will help out with the implementation to also making an implementation plan and documentation and how to implement this throughout all in situ TAC regions. So this work is now done at IMR in Norway, so we have chosen the Arctic as a focus area, and we will collaborate in the Mediterranean and Baltic regions with our partners to set it up and test it. And when it works, if it works, hopefully, then we can then implement it in all the other regions as well. So this will be done in close collaboration with the in situ TAC project team. And then last, we have a package on project administration. So this is really where I come in then. So if you have any technical questions, I will bring them on to the experts. But yeah. This is just schematic of what I just said actually. So when the data requirements are in place, then we move on to the next work package, and you can see we have 3 milestones. That the first one is that the data are collected and delivered, and the exploratory analysis is completed. Then we move on to the model development, and then as we approach halfway, we need to make a decision on which model to be used and for the implementation into the operational environment. And then we move on to the pilot deployment in work package 3, and then the final milestone towards the end of the project will then be a final model validation, and that it's tested and we can get it to work. And then we need to make a decision on the model to be used for regional implementation across the in situ TAC. We also have a list of, I would say, quite ambitious key performance indicators. They go on the method, the validity of the method, that we want to reduce the false positives and so on, compared to what we have today with typically range tests, spike tests, and so on. KPI on performance, on accuracy, and also guarantee that the data modes, and also the completeness of the training set, that the data represent the variability and diversity in the region. And I will come slightly back to this later, but this is an important point, of course. Consistency of the training set is important. We also have some KPIs on implementation, that we need to keep a constant performance of the model, so we need to check if there are trends. There can be trends in the data, and are they represented correctly and so on, and that the model is not drifting, maybe some retraining is needed. Operational readiness, we aim at TRL 5, and then also efficiency and scalability, of course, because even though we get this to work, if it takes like hours and hours to run this every day, then it cannot be run in an operational pipeline. So we have set a goal that the processing time should not exceed 60 minutes. So it's actually feasible to implement it in data pipelines like at the in situ TAC. Moving a bit to what kind of data we are actually looking at. So we are looking at CTD profile data. We start out with that and see if we can get that to work, and then we can build upon that later on. But that will come in additional work and additional projects and so on. So in this project, we're talking about profiles, here represented by temperature profiles. So here you see a map of all available profiles that we have located since 1980. You can see they are fairly well spread throughout the years in the graph to the lower left. Also throughout the year, you can see there's a good spread. If you're talking about geography, then you really see that some places or some areas are pretty densely sampled, some are really not densely sampled. The variability differs between regions and so on, so this needs to be taken into account, and this will affect how good the model will be, how easy it will be to train it, and so on. So these are really some challenges that we need to cope with here. So what we have started doing first is to map the data and provide maps for clustering the data. So that is the approach we will try here. And here you see to the right some examples where we have used 6 classes. And if you see the blow up of the northern Norwegian coast there, I think, at least for my part as an oceanographer in this region, it starts to look reasonable that yes, these are probably some kind of regions that I would draw as an oceanographer here. So these kind of different regions here or classes have things in common. So this at least looks promising that, okay, let's start training on these data in these regions and see if it works. But as you saw, the different regions here have very different data density. So we are very eager to see how that will go. I want to mention that we have collaboration outside AIQC, as I already said. We have collaboration with IQOD. I don't know how, am I on time? Yeah, then I can just see the headlines. We have close collaboration with a team at AVI, who are also working on AI-based QC. And I mean, this is really important, and we want to talk to others who are doing similar things, because resources are not very abundant, and so it means that we don't want to spend time and resources on doing things that others have already tried and failed at doing. So if people have experience that this is not working, at least, then that's very valuable to know. So we would like to collaborate with more people, if anybody is doing this. And yeah, just to mention future work, I've already said a lot of it. We will define subregions also for salinity, oxygen, and chlorophyll, as I just showed. We will try to create tailored subregions for the Baltic and Mediterranean Sea inside the project, and then afterwards we will move outside of that. Develop QC models using supervised machine learning for anomaly detection, and then deploy the models in a production environment. So I think with that, I thank you for your attention.
Thank you, Vidar. Thank you very much. So we will straight move to the next project, which is BGC Optique from Raphael.
Hello everyone, so my name is Raphael Sozed and I will present you now the BGC Optique project, which means biogeochemical Argo optimization data quality. So this project is led by the LOV, the Laboratory of Oceanography from Villefranche, from Sorbonne University, and in partnership with ACRI. We are people from the multi-ops stack, also from the Argo data management team, and from OCTAC. So the context is that the BGC Argo floats are delivering high-quality biogeochemical observations with an impressive spatial distribution and seasonal resolution. You can see on the graph the impressive increase of the observations from 4 EOVs from the Argo network compared to other observations that are here, the observations from the World Ocean Database. And it's corresponding basically, for example, for the chlorophyll A concentration and the particulate organic carbon observations to 17,000 profiles per year. So it's a lot of profiles arriving. And the BGC Argo data are available in Copernicus through the in situ TAC. in near real time, but also in delayed mode products. And there is also the availability of BGC Argo data from observation-based products that is delivered from the multi-hub stack. So it's based on a machine learning technique that derives the vertical distribution of particulate organic carbon and chlorophyll A concentration from the satellite data used as inputs. And it's based on a training using BGC Argo data. So next year there will also be the light available in this product, the radiometric variables. So the challenges of BGC Argo data are first the uncertainties in biooptical data transformation into biogeochemical variables. So the floats are measuring biooptical data, and we want biogeochemical variables. For example, we are measuring fluorescence of chlorophyll A, and we want to deliver through Argo the chlorophyll A concentration. So there are some adjustments to make. And there is also another challenge. So Argo is delivered through the Global Data Assembly Center, the GDAC, that is gathering the data from different DACs, so from different countries, the data assembly centers, and there can be some delays in the implementation through the different DACs, impacting the timeliness and the consistency of the data available in the GDAC. So this is where the project BGC Optic wants to improve the accessibility and the accuracy of BGC Argo data as part of the Copernicus Marine Service, so through two tags, the in situ and the multi-hub stacks. So there is an unusual work package 1 of management and coordination. The work package 2 aims to improve the chlorophyll A concentration BGC Argo dataset. So it's a focus on the chlorophyll A concentration. The work package 3 aims to develop some statistics for the qualification and the improvement of the BGC Argo dataset. So for all biooptical data from BGC Argo that are also measured from ocean color, so chlorophyll A concentration, particulate organic carbon through the backscattering coefficient, and the radiometric variables. And the work package 4 is about the uncertainties quantification of BGC Argo data. So a little bit more in details for the work package 2 that aims to improve the BGC Argo chlorophyll A dataset. We will use machine learning. I will detail this how after. So the context is that the BGC Argo floats measure the fluorescence of chlorophyll A that we want to transform into chlorophyll A concentration. However, the relationship between the fluorescence and the chlorophyll A concentration is really complex and depends on first the phytoplankton community composition and also the physiological state of the phytoplankton that varies upon regions, vertically and so on. So in the Argo data stream, the fluorescence is calibrated into chlorophyll A concentration using 3 corrections. I won't go really into details, but I will be happy to answer your questions if you have. You have the dark correction that is a sensor-specific adjustment. Also the non-photochemical quenching correction, that is a physiological adjustment to account for light-induced quenching effects. So it corresponds to an effect that is near the surface at high irradiance. And physiological ratio correction that addresses both variations in phytoplankton community composition and physiology. So the ADMT, the Argo Data Management Team, focus on improving this correction by testing new methods, both in real time and in delayed mode. However, qualifying the improvement of specific corrections is quite challenging because we don't have a lot of correspondence of BGC Argo float profiles and reference in situ measurements. So that's where we propose a machine learning-based workflow that is based on the SOCA method to emulate BGC Argo measurements against the reference in situ HPLC data that will allow us to compare different corrections at the global scale. So the idea is to run different SOCA model using different data set of training based on different corrections. And the one with the best statistics when compared to the HPLC in situ measurements will correspond to the data set the most accurate. So it will allow to evaluate the different corrections and to see which one is the best to apply. Then we have the work package 3 about the refinement and the development of methodologies for the quality control. So for now, which is operational for the BGC Argo community is the flagging of anomalous profiles of backscattering coefficient, the BBP, which is the estimator of particulate organic carbon. And it's released to the Argo community since June 2021 yearly. This flagging is available through comparison between the observations, so the BGC Argo float profiles, and a reference data set that comes from a SOCA neural network and that is delivered actually from the multi-hub stack from Copernicus Marine Service. So the idea here is to improve this flagging by developing it for the other biooptical parameters, so the radiometric variables, the light, and the chlorophyll A concentration, to improve the statistics for flagging the bad profiles, for example, using the time series of the float instead of comparing on a profile-by-profile basis, and, for example, focusing on specific layers of interest. We want also to use ocean color in addition to the SOCA-based reference that will be used for a reference for a surface comparison. There is, after the work package 4, that will be led by ACRI on the optical measurement uncertainty estimates to support quality control. So the BGC Argo uncertainty estimates will be developed from the triple collocation method. So for chlorophyll A concentration, for example, there will be the use of 3 different data, the BGC Argo, the satellite, and model data. For BBP, it will be BGC Argo, satellite, and LIDAR, and different options will be tested for radiometric variables through, for example, the KD validation or PAR validation, because we don't have it directly from ocean color data. There will be the development of a visual web tool in support of the quality control. So we will have accessible the profiles with the uncertainties delivered from this triple collocation method. And it will provide the matchups between the BGC Argo data and the satellite data. It will allow also to display float time series. And so it will help to QC the profiles also. So what we expect to be the impact on the Copernicus Marine Service, it's first to improve the accuracy of the chlorophyll A concentration data through the Argo GDAC or directly within the Copernicus in situ TAC. We want to update also the quality flags for all the BGC Argo biooptical data through the operational implementation of the flagging of anomalous profiles through the in situ TAC. Then the better BGC Argo datasets will enhance the quality of the multi-hub 3D SOCA-derived products because we will have better datasets to train on. And finally, a better estimate of BGC Argo uncertainties are essential for data simulation in biogeochemical models. So finally, improving the BGC Argo data accuracy and uncertainties is critical for the modeling community and will hopefully contribute to the future development of the ocean digital twin. And thank you.
Thank you, Raphael. So we now move to the next project, which is presented by Luca and which is called Globio.
Okay, thank you. I am Luca Manzano. I will present this Globio, bridging global and local scales in biogeochemical profile prediction. What's the idea of this project is to use machine learning techniques to reconstruct BGC IGO profiles, but in particular to create a global model that can be specialized to multiple regional or local models in a semi-automatic way. More in details, we will start by, and we want to develop and improve the current state-of-the-art machine learning methods using neural networks to reconstruct biogeochemical profiles and, well, release the corresponding software to build both global and regional models. But also we want to develop a way to transfer the knowledge acquired by the global model that can be trained on a lot more data to regional models, specialized regional models that can take advantage both of regional data and of the large amount of global data. Clearly, without any indication of the uncertainty of data, then the usefulness is limited, so we also want to use uncertainty estimation methods that are commonly used for neural networks also in the building these tools. Those methods can be both the standard ones, like ensemble methods or Monte Carlo Depart, but also new ones developed for this, and develop not only the software to perform this transfer from global to local, but also a set of best practices. That is, when can this transfer happen? When do we have enough data for this transfer to be, say, a successful one? Well, that's all the goal that we want to attain with this project. So, why to use neural network and not other techniques? Well, the classical reason are because machine learning techniques and neural network in particular can automatically discover patterns when we have a large amount of data, patterns that may not be visible with other methods, but also to reconstruct incomplete or missing data and work with multivariate dataset. But also, if we use more modern architectures, not only the multivariate bisetter, but also convolutional networks or transformers, we can use those techniques to also capture spatial and temporal patterns, potentially improving the accuracy of the reconstruction. And we can use also transfer learning techniques to adapt a trained model to one specific region. What we currently have is PPCON, which is working on the for the Mediterranean Sea. When we work with the convolutional networks, taking as input the profiles of some of the variables and constructing profiles of unobserved variables in a, say, pretty effective way. In fact, it is already used, and you can actually see how the reconstruction works at the website. But this model is only for the Mediterranean. Clearly, we need something more. And not only to perform what we call direct profile reconstruction, that study from temperature, salinity, and oxygen, reconstruct chlorophyll, nitrate, AP700 and the pH, but also to provide the reconstructed profiles as input for other methods and other techniques. So, what are we doing, what we have done, and what we plan to do? So, we have built collected data set to perform the training of the network. And we are currently working on the design of the network architecture. We can use, and we will start from the already existing PPCon network, but since we are working with a lot more data, with a lot more variability, we also want to adapt the architecture and use other techniques like new evolutionary techniques to try to improve the architecture of the network. Then we can perform a full training and evaluation of the different architectures to find which ones are the best suited for the profile construction, and also add the component for uncertainty estimation. But the next step is, I would say, the most interesting one from my point of view, that is build from this global model a set of regional models, testing on some case studies, and also finding when we can perform this construction. So what we have is currently the global dataset, and as I said, we are working on adapting the network architecture. And what do we plan as impact for all of this? And well, first of all, I see this as a first step as a model as a service. That is the idea that we can say, I have those data, can we specialize the global model to those data? Yes, we can do it automatically under some conditions. It will not be completely automatic, but let's say simplify the building of new machine learning models for profiler construction, thus improving all the quality of biogeochemical forecast and analysis. This can help in the design of the Argonne and BGC Argonne network, and in general increase all the spatial and temporal coverage of the data. And as I say, we also plan to release and have people work with the models and the procedures that we are developing. So I try to be brief. So let's finish with the team. The team is, let's say, quite heterogeneous. From the University of Trieste, where I'm from, we are work mainly on machine learning, and clearly OGS when they work clearly on oceanography. So we are collaborating on this, let's say, interdisciplinary aspect. So as a computer scientist, I have to understand how BCC Argonne works, and I have to explain how to work with machine learning methods. So thank you for your attention. I hope it was interesting.
Thank you, Luca. So now we move to the last presentation of this first session with Hong Yang and phytoplankton functional type product for the Arctic Ocean.
Yeah. Oh, thank you, Stephanie, for the nice photo. Okay. Hello, I'm Hong Yan. I work at Alfred Wegener Institute in Bremerhaven in Germany. And today I would like to introduce to you our project with the Copernicus Marine Evolution Project, the ML-Phytol, which is the machine learning-based approach towards the products of phytoplankton functional types in the Arctic Ocean. It's good to know that the previous 3 projects were also got machine learning involved, so that we can also learn from each other and get improved in our techniques. So this project actually is a collaborative project between AVI and ACRI-ST. So we have in our team 6 members. I'm the lead of the project, and from the ACRI side we have Aurélien Prat for the lead from the ACRI side to support us with the data, the matchup extraction, and also maybe big data processing, etc. And we have 4 other supporting experts, Astrid Baha, which is the group leader of my working group right now at AVI, and also we have a PhD student who is dealing with the data science very professionally. Asa Medifor, he's doing his final year of the PhD, and hopefully he will stay also work for us on the ML-Fatal project. And then Marine and also Antoine from ArcST, we have been collaborating for quite a long time, since 2018 or 19, when we got involved into the Copernicus PFT products. So since 2020, we have our PFT global products available on the Copernicus marine surface, and right now we are trying to always update and improve the product on the Copernicus marine surface. That's why we come to this ML-Fatal for the Arctic Ocean. So the overall goal of the project is to employ the marine big data driven machine learning methods to set up the improved retrieval approach for the phytoplankton functional types. And at the end, we are hoping to deliver the gap-free products for the several key PFTs to complement the current ocean color and also biogeochemical data sets for the Arctic Ocean. So here shows the Arctic Ocean, the PFT distributions, including also the total chlorophyll, and you have the diatom distribution, and also the nanoflagellates, which are the sum of a few other groups with smaller sizes. So this is a 10 years mean, and if you look at actually individual images, they are really gappy. That's why, so we have the motivation for this project. So firstly, it's the needs for the product to be evaluated. So the evolution and improvements in the PFT product for the Arctic Ocean are really required because of the high uncertainty in the PFT data in the polar regions. If you look at the map on the upper panel, so we have the diatom uncertainty map here, which are also available on the Copernicus marine surface. We have the per pixel uncertainties for our global PFT products, but for the higher latitudes, you will see very high uncertainty for most of the phytoplankton groups, and which lowers the quality of the PFT product in this region. And also we are lacking of high-resolution gap-free biogeochemical products in the Arctic Ocean. And here the map lower panel shows the diatom chlorophyll in July from 2003 to 2023. And it shows also, this is already the monthly map, and it shows also in many regions we don't have data there. So we are also trying to apply a gap filling technique to really deliver the gap-free product for the Arctic Ocean on the phytoplankton functional types. And with all these outcome, I think from Copernicus marine side and also from our own research, we get the benefits on the firstly is to complement the current data catalog in the perspective of the Arctic biogeochemistry. And also we try to deliver a showcase and first example of the big data driven learning techniques for the European digital twin of the ocean by providing the quality assured data. And then it can also stimulate the cutting edge research for understanding better the contemporary state of the phytoplankton in the Arctic Ocean. Because right now the time series study on the phytoplankton groups on the regional scales and also global scales are also really a hot research point. So our objectives, so by knowing of all the needs, so we try to firstly develop a marine big data driven learning approach specifically for the Arctic PFT monitoring, ideally from only May to September, so it's only the early summer until the early autumn season using multi-source marine data. That's because the ocean color satellite data can only cover during these months, and in wintertime we have no chance to get ocean color products there. And the second step is the objective is to evaluate the Arctic PFT data with our highly resolved underway optical data and provide a solid uncertainty assessment. And then we are going to deliver the gap-free long-term PFT products in the Arctic Ocean open waters by applying the DIN-KAI method, which was developed by Alex from University of Liège. And we had also collaboration before with them regarding this gap filling technique on DIN EOF, and right now also DIN-KAI. Our PhD student Isan was closely collaborating with them. And finally, we try to promote these PFT observations to the Copernicus Marine Surface through the OC tag and to complement the current ocean color data for the Arctic Ocean. So we have basically from model development, then we do the evaluation on the data, on the product, and then we do the gap filling as well, and then finally it goes to the operational stage. So regarding the work packages, we have basically 4 work packages, and the work package 4 is mainly the management, which is on top of the other 3. And the work package 1 includes the data acquisition and curation. So we have collected in last years, since 1997, the institute data set on the PFT, and we will do the pre-processing on them, and then we also need to do updates, since there are also some new data sets released, and within our internal contact and also the public available data set, we have to still update the data set, which is mostly done right now. And then we need to match the institute data with the satellite data and also the product from the Copernicus Marine Surface to get really a match-up data set for our training. And then when the data preparation is done, we will try to do different experiments on the machine learning techniques to try different machine learning methods, trying to finally develop and also deliver an ensemble training set for the ML5 tau. Then the evaluation and uncertainty assessment will be also included in the work package 2. And finally, in the work package 3, we will try to apply the DIN-KAI, which is also based on the neural network training to fill the gaps on the product to deliver the finally gap-free product of the Arctic Ocean on the PFTs. Then with all these packages, so currently we just started with the with this project. So we had the kickoff meeting in September, late September, and right now we are in the first phase in the work package 1 by preparing all the data. So regarding the data for training, we try to use all the data that are available on Copernicus Marine Surface because that would be, very convenient for us to really apply the model into the Copernicus Marine Surface for the final implementation. So make that everything easier. So we choose on the Copernicus Marine Surface different data sets, including the bio-optics, the ocean color data set, and also the BGC data set, including different nutrients, and also the biogeochemistry and physics simulated products from Copernicus Marine Surface. So they have different spatial resolution. So we have to do also pre-processing before we really get the match-up data set. We probably need to do the interpolation and also resampling on the data set to make sure that they are in the same grading. So the data creation, right now for the institute data we have in the Arctic region, we have collected in the last 25 years over 3,000 points of the institute PFT data. So it's not like the chlorophyll data, we have really a large data set on the global scale or even in the Arctic. But for the PFT data, we are purely based on the HPLC measurements, which are really limited. But right now we have collected already over 3,000. And then we have also, at AVI, we have always the Arctic expeditions with our icebreaker Polarstern. So since 2015, we have always the expeditions in the Arctic. So we are collecting data with the ACS, which give us the hyperspectral absorption data of the phytoplankton, so that we can get also the phytoplankton information by using the biooptical models we have developed. And with that, we have an overview of this model development. We have the data from the Copernicus Marine Service. We do the feature selections, and then we do the matchup process by comparing to our institute measurements, and through a series of pre-processing and data preparation, we do the training test on the data set by using different machine learning models. Finally, we will come up with an ensemble by integrating different machine learning models to get the final output of the PFT. Also through a series of validation, which will be the final output of the whole project regarding the model development part. So we are currently here at the months 4 and 5, and we are still at the data processing stage, and hopefully soon we can also start to test the different methods using machine learning techniques. I think, that's all. And then in the future, I hope we can have a close collaboration with the other, OCTACs and also other MFSCs, trying to improve, all the communication and cooperation to improve the whole project in terms of methods and also the deliverables. Yeah, thank you very much.
Thank you, Hong-Yan. Thank you. So we have like 5 minutes for a short Q&A session. So I don't know if there are questions in the room for one of the speakers. No questions, not yet. Okay. There's one on Slido, okay. Okay, there's one for Vidar. Where do you plan to deploy the model? What technologies, workflow are you considering also for serving the model? Okay.
Yeah, so regarding, you hear me? Regarding where we want to deploy it, as I said, we will first, when we have a pilot, we will deploy that at IMR in our own data pipelines, our own operational pipeline, which also feeds into the in-situ TAC, of course. And then we will deploy it across other partners in in-situ TAC eventually. So that is the plan.
Okay, thank you. Maybe if you can go to the Slido and also answer online so that we have question and answers recorded. Thanks. Okay, so if there's no additional question, we can move to the next session, which will we will stay in the Arctic Ocean. So the session is about improved Arctic prediction, as well as on AI-based forecast. And I leave the floor to Stephanie for the first project, which is called Arctic Bliss.
Hi, everyone. Do you hear me in the back? No? Yes? Okay. Thank you. So I'm Stéphanie Leroux, research scientist at Atlas in Grenoble, France. And I will present Arctic Bliss, so that started a few months ago. It's a collaboration with different colleagues that you can see here. Colleagues from the Nansen Center in Bergen, Norway, from IGE, and from INRIA in Grenoble, France. So in short, Arctic Bliss is about sea ice forecasting. And our goal is to document the short-term predictability of sea ice, and especially sea ice drift, in a state-of-the-art model, prototype model, that will consider altogether 3 new elements. an elasto-brittle rheology. So that's the way to represent sea ice mechanics. I will show an illustration in the next slide. Two-way coupling with an atmospheric boundary layer model, and an ensemble modeling framework that will allow for probabilistic or ensemble forecast. So those bricks, they exist already, but either they are not used yet in the operational systems in the MFCs, or if they are, it's never all together. So the goal is to have a prototype that has the three and evaluate or assess predictability in this context. So I will come back to those three aspects now. So the first one, elasto-brittle rheology. So as I said, it's a way to represent the mechanical behavior of sea ice in the model. And this elasto-brittle rheology is a way to better represent sea ice deformation with, I should click, yes. More localized in space and time, as we expect from looking at observations, and in particular scaling laws of deformation. So that's the plot on the right, but I don't go too much into details here. The movie shows the same model, but with two different rheologies. BBM, so elasto-brittle on the right, versus the standard rheology used in the same model, so elasto-viscoplastic. And you see on the right that the features are much more sharp in terms of the deformation. So this rheology is already in use in the operational NAXIMEF platform, the standalone sea ice model that is operated at, or by the Arctic MFC. But it was not available in NEMO CISQ platform until very recently. Last year, a colleague of mine implemented this rheology in the NEMO CISQ platform, and this is in this context that we will work in this project. The second element is a two-way coupling with an atmospheric boundary layer. So why do we want that? We know that the wind is one of the main drivers for sea ice dynamics on submersible skates. It explains a big part of the sea ice velocity variance. But in standard forced model, the atmosphere is always prescribed to the sea ice, and the atmosphere doesn't adjust to the sea ice state. So it's a big assumption we do here with inconsistency, potentially, between the atmosphere at the surface and the sea ice state. However, we also know that prescribed sea ice surface conditions can have an impact on the polar atmospheric boundary layer that was, it's documented in the literature. So here we want to have the two ways, so the interactions between the two. And we want to see if when you have interactions, it feedbacks on the sea ice dynamics and its predictability. So to do that, we want to make use of an ABL model that exists already within the NEMO CISQ platform. It was developed a couple of years ago by Florian Lemarié and colleagues. And very briefly, it simulates turbulent winds and temperature and humidity in the first 2 kilometers above the surface, instead of having the prescription of the forcing. And this ABL is driven on top of the ABL by large-scale usual forcing. Okay. Third element, the ensemble modeling framework. So we want to produce ensemble forecasts. So I should say HINCAS, because here we will forecast the past, but a set of ensemble forecasts, let's say, taking into account potential errors in the initial conditions. So we will perturb initial conditions to take this into account. And we will focus on initial errors in the position of the sea ice features. It's a way to represent the fact that initial conditions in operation forecast are never perfect because of errors in or lack of coverage of observations and errors in the data assimilation system and so on. With those ensemble forecasts, we will consider perfect sea ice model and take one member as a pseudo-truth, the rest of the members as as the forecast, and we can loop on the members like that. And using given metrics, we will assess predictability in a practical way. So it's like investigating the question, how much can the ensemble forecast be accurate for this given metric, and considering a certain amount of initial error that we know is there. And we will do that with and without an interactive ABL to see how the interactive ABL can impact the predictability. So in the end, what we want to do with this project is document and provide some information, some guidance for potential future updates of the operational systems in the MFCs that are dealing with sea ice. So just quickly to remind everybody that there are 3 MFCs dealing with sea ice, so the global, the Arctic, and the Baltic. Timeline, so we are here. So as the others said already, it's the beginning of those projects, so it's only 4 months since the kickoff. So in the meantime, we have hired Laurin Fiol to work with us on the project. And so far, we have worked on setting up the ensemble model, run test experiments, and we are working on preparing the probabilistic matrix. So I can show a few illustrations of those aspects. Here from a test experiment with our system, so with this elastobrittle rheology and the ABL module activated. Can I see this? Yes. So sea ice concentration snapshot here, and with this elastobrittle rheology, we have those leads that open. If you look at the zoom now, and you look at surface wind speed in the boundary layer, you see that it has adjusted to the sea ice state. There are those slight increase in the wind speed above the leads. If you look at all the values and you plot the distribution, you also see that when you activate the ABL versus in an experiment where there is no ABL, you don't change much the mean of the surface wind values, but you extend the tail, so more high values of wind speed when you activate this. And also you increase a bit the variance in the high frequency of the wind speed. So when you activate the ABL, the wind and the other variables, they adjust to the sea ice state. And then the next step is to see if it has an impact on the sea ice drift predictability. We've been also working on representing the initial error in the sea ice fields, as I said. So for that, in this project, we have developed this Python package with Jean-Michel Brancard at GE. I won't go into the details, but the idea is that it's like distorting a bit the initial feeds in the sea ice to represent the fact that maybe the assimilation system will do its job, but put the features not exactly where they should be. And this is an illustration of what we can do now with this package. So sea ice concentration, sea ice velocity in one initial state, in one member that has been perturbed. And the bottom row shows the difference between 2 members. So basically, the different members, they will all look a bit like that, but with the features, the leads here, that are slightly displaced. That's why you see the pink and the blue. You see the same in the sea ice velocity. And we can tune the amplitude of this slight shift. So here it's an example where the average positional error is about 10 kilometers, so 1 grid point, it's small. Because our system is at 1/4 of a degree resolution, so it's about 10 kilometers per grid point. And on the right, it's a larger error with 50 kilometers, and you see that the shift is a bit larger. So with that, we will initialize the ensemble forecast and assess the predictability, as I said. And last slide, we are also working on preparing the probabilistic matrix. So Laurin is doing that at the moment. So we will have the usual like CRPS scores, but also probabilistic score on the sea ice edge position, some probability maps for a given event, and probabilistic scores on Lagrangian trajectories that we can generate offline from our ensemble simulations. So next year, I will show more results, I promise. And I stop here. If you have questions, you can contact me or see me afterwards. Thank you.
Thank you, Stéphanie. So now we move to the next. Oh,
non.
Ah non, fallait pas faire échapper. Ah non, non, c'était next slide, mais ok, ben là je sais pas ce qu'il faut faire. Ok, Vincent. So please don't push the escape. So we will have the next talk in a minute. Dorothea with CCAP.
C'est celui-là? Ah, pardon. One sec.
I'll just use arrows.
As you wish. I will show you. One sec. You can use arrow or that.
One
Second.
Yeah, I'll say. That's good. So it's Dorothea Jovino speaking from CIMCC. I'm coordinating the CCAP Service Evolution project together with the GPINC-C8 Nansen Center that is with this team collaborating to this idea to have a better simulation of CIs in the Copernicus product, so mainly for short-term forecast prediction, but also for the analysis. So the main goal of the project is to deliver some seamless calibration tools that can be applied, in this case, to one CIS model that the product that we're going to use are sharing. But actually, can be the idea is that the tools that we provide can be then easily applied to any others CIS model, whatever is the complexity of the application that you have. In the end, we will have two different algorithms based on two different approaches. The green function that we applied by CIMCC to the SEAGLORS system that we use for running the global ocean reanalysis, and Andrej Polone that is sitting here is in charge of that. And then those AES, the dual one-step head ensemble smoother that will be applied to TOPAZ by the Nansen Center. And together with that, we have built an archive of CIS data that, of course, goes together with the talk that we have on the Arctic, that will also include some data on the Southern Ocean, since we also have a global simulation here that for now is shared between CIMCC and NERSC, that then will be available actually for everyone in the end of the project. So the motivation for that is actually given by the picture that you have there on the slide. It's mainly how the Arctic looks like for a large part of the year now. So the current CI state is kind of moving to a situation where the marginalized zone is dominating for a big part of the year. So here you only have plots based on observation, satellite observation, and the decline of CIs is pretty visible if you look the upper, probably I have the, yeah. If you look at the time series here of the CIs extents, that means the CIS has absolutely negative trend into the Arctic with a lot of record lows that we experienced in September, mainly in the last 10, 15 years. And that means that actually the structure of CIS into the Arctic also changed. So what we have is this kind of a picture. We go in time toward the loss of multi-arisal ice with the domination of young ice. That means
thinner ice, more permeable ice that's also open, more open ocean that can communicate with the atmosphere. So in this situation, how our model actually can reproduce these new states. Here you have actually an analysis that we have done at CMCC based on Copernicus product. You have a graph-based ensemble mean of the global reanalysis. You have PyMS, that is not product delivered by Copernicus, but is kind of used as reference for sea ice variables into the Arctic topaz that's been presented by Laurent yesterday. And then there are two data sets of satellite observation. Here we're looking again to sea ice area. That's pretty similar to sea ice extent that we saw before. You have all the different products. They align pretty well in March, and they also have the same trend in September. Actually, I like to say that outlier here is PyMS. And then you have the seasonal cycle on the other side. And also in this case, if you look at the top plot, the seasonal cycle is pretty similar among all products, and the plot in the bottom, the panel on the bottom, show actually difference between the last GADEC and the first one that Copernicus provided, and then you see that actually there is kind of decrease in sea ice area through the time. So everything seems kind of well reproduced and consistent with observation, but then if we move to metrics that dig a bit into the details of sea ice characteristic, what I'm showing here is exactly the same plots, but just for one ice class. So we are looking here only at the marginalized zone, and then what is very simple to see if that's the agreements among products is absolutely lost in this case. So even observation doesn't have the same variability in time. That's kind of a good point for the ArcTac. But also the ensemble mean, the global ensemble mean, topaz, and PyMS actually don't follow the same internal variability. Also in this case, PyMS is the one that is largely overestimating, at least compared to the others in summer with the marginalized zone, how the marginal zone is represented. Also looking at the seasonal cycle, so the histogram here, you see that the disagreement that you have among observation is the two last line, the green and orange, is pretty large, and it's pretty similar to what's also the different modeling products are actually reproducing. So if we dig a bit more into the sea ice characteristic, the product that we use generally for assess the sea ice states and variability into the Arctic are not that accurate any longer, and situation gets even worse if we leave the sea ice concentration parameters base, then we go to see other variables as sea ice thickness. There is not assimilating into any of the system beside PyMS. Beside PyMS, at least in this version, for the last 10 years, if I remember correctly, Ron. And then you see that the blue shading area is actually the spread among the 4 GREP members that gets very large. The trend is not captured by some products. And also the very caveat that we have here is that we have no observation for thickness. So you see that there is only the CryoSats product, is match product of satellite data that covers also only partially the time series, only for a few months here. So the idea is to work on the sea ice model, not improving the physics and increase the complexity, but just try to tune or calibrate them to also reproduce this kind of a process in a better way. So why 2 different algorithms? Mainly because the first one, the green function that we're going to use is simple. The complex one and more sophisticated will be run by the Nansen Center. Mainly because the 2 applies really well to the different products that we're using. So the green function is kind of is our best thought for reanalysis, so long time series, while the dual one step ahead ensemble smoother applies pretty well to the topaz philosophy with ensemble data simulation schemes. What we will have in the end is 2 different products applied to the same model with kind of similar system in terms of complexity of the model itself, different ocean by same atmospheric forcing. So what we want to see is if we go independently in calibrate the same model for different application, how close the results will be. if the optimization that we have in the end is comparable between the two methods, and mainly, as Mercator suggests, to see if we apply one calibration to another model, what happens. You have a scheme there of a few variables that cover a different part of the CI's code, so the radiation scheme, the thickness discretization, dynamics, and thermodynamics. That's our first guess, so we will start with those parameters, so it's albedo, some of the key dynamical parameters. That's what is generally actually tuned by users when you run the CI's model. Then we will also add, of course, the picture can be very complex. We can add many other, we will add many other parameters, mainly the one they are missing here. They are relating to the coupling between CIs and atmosphere. Stephanie just show how that is important. So pretty quickly into the two schemes. I'm not going into details. So here we have the schematic of what Nansen Center is going to use. So the framework is in this case, is dual. That means that we have the computation of one step ahead ensembles, where both at the same time the model states and the parameter that we want to calibrate are both adjusted, and then we run the second optimized simulations. While in the case of in the case of the Green function, here we go, the approach is much different. So we will have less simulation, because in this case we have, for any runs, we have under members to run ensemble. That means that simulation needs to be much shorter for the lack of resources. So this kind of studies applies really well to forecast and short-term prediction. While in our case, we will be based on the new version of SIGLOR, so version 8 that will be released soon. We will use that as the spin-up of our study, and then from, let's say, 2000 or any year close to the current states, we'll start running sensitivity experiments. I'm done. It's 10 or double number, but those are going to be kind of 10-year simulation. So we will test actually the calibration on a longer time scales. But the main difference that we have here, that in this case, we just optimize one parameters each time for any simulation, while into the other case, all the parameters can randomly be run together. In the end, there is the cost function that tries to minimize the difference between the model and the outputs. So the things that we have done so far, besides deciding the parameters that we will start using in our calibration, we have also discussed a lot on the observation that we have to use, both for calibrating the system, but also for the validation with independent data afterwards. So of course, we have data that Copernicus provides, but we also have collect some other data sets that both Shipping and myself are already using. We have put that was the delivery of the project. We have an archive system, SMCC, the DDS is the data delivery system, that now is collecting those data sets. They are sharing the same grids, covering more or less the same periods. We have interpolated them on a 6-kilometer grids. That is much closer to what TOPAZ does, but of course fits for validation also for the course resolution that we have in the global run. And that's also, as Copernicus is doing, we have switched from NetCDF files to ZAR files. That makes the memory usage much lower, even though those data sets are only 2D, so it's not really heavy, but that makes actually the operation on the system pretty easy. The system at the moment is down because we are migrating from the old machine to the new one, but we hope that in the middle of February will be everything set up and running. I'm done.
Thank you, Dorothea. So we now move to IceCastNet with Julien.
Thank you, Stephanie. Hello, everyone. So this is me, Julien Brajar. I'm from NERSC, and I'm leading this project called IceCastNet, which is about doing sea ice forecasting based on AI. So this is a team beautiful team involved in this project. So if you see some of them here or where you can talk about them, about the project, of course. So it has been shown by Dorothea just now that CI's forecasts, they are biased and they have some errors. We can also say that CI forecasts, they are quite costly to run, and sometimes they are also at too low resolution. And actually for all those problems, so the cost, the bias, and the resolution, there are some evidence that artificial intelligence can help. So I won't go into all the details on how it can help, but you can have a look at all those papers or talk to me after the session. We can discuss hours about that. So the idea of the IceCastNet project is to basically combine all those demonstrations that AI artificial intelligence can run cheap simulation of CI's dynamics, can reduce the bias, and can run also at high resolution, blend all that together and produce a data-driven AI forecast at high resolution for the CIs. So with no CI's physical model involved anymore. And it will be at high resolution up to 10 days forecast. So the purpose of this project, IceCastNet, is to demonstrate that we can achieve this purely AI forecast. So what is the approach we have decided to go through? So what is a forecast? Basically, you take some field. So we take a field that is observed, so an observable product, such as here, this is a CI thickness from CS2Smos, also showed by Dorothea. And we will learn a data-driven model to do a forecast at time t plus 1 day, also on the CI thickness. And also we also have the same thing for concentration and drift. And we will roll out this process, so it's an autoregressive process, up to 10 days. So if we use only observational-based product, we have a forecast at quite a low resolution, and also this approach is known to smooth the forecast. So on top of that, we will add a physical constraint super resolution algorithm. So here there is some physical model involved to train the high resolution field, and we will produce for each of the low-resolution data-driven forecast, an ensemble of high-resolution, physically constrained forecast. So this is again an example with CI thickness, but we do that with three variables: drift, thickness, and concentration. So where we are now, we have some preliminary experiment for this first step of the data-driven forecast that we are going to show you. It's really preliminary. So actually, a thing I would like also, if you have some ideas or comment or feedback about the result I'm going to show, please come to me. I will be more than happy to discuss. I have nothing planned tonight, so you can come to me. And in the second year, we will mostly focus on this high-resolution downscaling. So the data we are using, I won't detail it too much. It's only observational data, except for the CI thickness in summer when we use Topaz analysis. And we did the first work of interpolating all that on the same grid and just distributing the data to have our training set for the first step. We also used some forcing from ECMWF, some wind forcing. And we have divided our data into training, evaluation, which is basically validation, and production, which is basically test, but we will try to demonstrate that we can run semi-operationally this product. So this is the choice we've made because of change in processing in the ECMWF forecast. So to have like a consistent data set over time. So here's the first result. So I will maybe go a little bit through it. So we used to do that a machine learning model which is called a UNet, which is based on convolutional neural networks, a relatively small one with almost 2 million of parameters. And so what we do here, so these are the input of the method at times t, so the drift here, dx dy, the CI concentration, the CI thickness, and the atmospheric forcing. And this is here the prediction we do, and this is the ground truth, so the labeled data, the observation data of the same time. So maybe it's not very clear here what we get. It's maybe clearer if we look at increment. So increment is the difference between the T1 and the T0. And you can see that this is the first training that has been done. So it's really, again, we have to tune that and go a bit further. But we see that we do some pretty good job for the drift, because this is what we predict and this is what is the truth. It's okay-ish for the sea ice concentration, because on the sea ice edge we are pretty good. We predict well the increasing of the sea ice extent. Sorry, the increasing of the sea ice extent. But we have some bias in the pack ice with a negative bias, so we still investigate that. Also, as I said, the idea is to provide forecast over 10 days, so we can roll out this prediction over 10 days, and this is what we get. So this is basically the first data-driven sea ice forecast using AI. Still to be improved, but up to 5 days we are good on the drift. And you can see there is a problem with the sea ice concentration that should not decrease, and this is due to this negative bias. So we still investigate that. Again, if you have ideas on how to solve that, very happy to discuss. So this is the same view, but with the error given with respect with the lead time. If you want to go through all the graph, you can, but the take-home message here is that we are improving a lot compared with persistence for the drift, not yet for the concentration and thickness. Again, this is work in progress. So, parallel to that, we also have think of using another framework to do this work, which is a toolbox or framework called Anemoy, and that has been developed by the ECMWF to do exactly what we do, but for the atmosphere, to do this AI weather forecast. And it's a framework that is used so far also at ECMWF, Met Norway, and other institutes. It's free, it's very nice. And we also think of using this framework, and also this is something I want to discuss, if you are happy with, to discuss, okay, what common tools could be used when it comes to do data-driven forecast. And maybe this one can be one. Of course, there are pros and cons to do that. So what is good is that we can benefit of all the state-of-the-art machine learning models that are developed at ECMWF to do forecasts, so graph-based, transformer-based model. Also, when we want to share our models, it's really facilitated. It's really optimized, efficient, and when we want to go to production, it will always facilitate it. And also, it will we will contribute to enlarging this Anemoy framework, so it can be useful to have a common framework for this type of problem. Some problems still, it seems that we are not sure that we can solve easily. Some very simple machine learning-based architecture are not available in this framework so far. So UNet that we are used, as I showed you, is not available. It's a bit, of course, less flexible than what we are used to develop with. And for the second part, if you remember, I want to do downscaling, and I didn't mention it, but I want to use a particular machine learning model, which is called diffusion model. And which is not yet available on Anemoy, but maybe it's coming. So just to see if it was possible, we did a first training of Anemoy. It's still not working so well because there is, for example, problem with NaN data when there is no ice or sea ice thickness to 0. So we still investigate that, but actually we are able to do from data pre-processing training and forecast with this framework. We still need to improve some technical details, but the basic flow is working. If someone, okay, I'm repeating myself a lot, sorry, but if someone knows about this, very happy to talk. And basically this is it. So now what we have to do is to decide on this framework. Should we use Anemoy or not? We should now improve and tune our model to improve our forecast, develop the super resolution approach or the downscaling approach in the second year, and apply validation tools. So I think that in other Copernicus marine evolution projects, there are some plan to develop these validation tools. So I think that would be some also good idea to share some ideas on that. And we will propose a demonstration of this in the pre-operational context, showing that it could be applied. So you can have CIS forecast very cheap at high resolution. Thank you very much.
Thank you, Julien. So we go now to the next presentation, so by Ronan, still AI-based forecast, but of ocean variables.
Okay. Good afternoon, everyone. So I'm Ronan Fablet. I'm from IMT Atlantic, and so I will give a short presentation of this project, so somewhat related to forecasting topics with AI, similar to Julien, but here we'll target like global scale and ocean variable, focusing more on simplified representation of the ocean first. So here you have two photos of myself, and you probably see that I'm not the blonde lady here. And so Daria is in the room. She's the co-I of the project and a postdoc in my team. Okay, so so first the team for this project. So we have on one side the Odyssey team, which is a joint research team between INERIA, IFREMER, CNRS, and IMT Atlantic. So on basically the interface between ocean numerics and AI, to make it short, and ocean observation, and comprehensive expertise from Ocean Data Lab and the IG, Julien Le Sommer especially. And you have the name of the different key people working in the project. So basically, what's the goal here? So we address one of the key priorities of the CMEM's call, so regarding the development of AI-based ocean forecasting. Here the goal, as I said, is to address the ocean forecasting global scale and to demonstrate or to assess whether using AI we could have similar performance or even outperform operational system. And on our side, we rely on the previous expertise on deploying AI for neural mapping that was shown this morning by Jan. And we think we can transfer this expertise to ocean forecasting, and that's the goal. And at the same time, that was mentioned by Jan this morning, there's quite some new activity on related topics, and Jan mentioned this morning the GLONET, which is a new model developed for ocean emulation, or the emulation of ocean model, and that could be used for ocean forecasting. And you may have heard also of Shire, a Chinese ocean model based on AI. So those would be like baselines we'd like to compare with for the specific experiment we want to address. So maybe what we want to address is we want to build a machine learning scheme, so a deep learning scheme, able to map some observation data, here just illustrated for altimetry data, but we would like to use satellite derived observation data, Argo data, as inputs to a deep learning scheme, so that as output you get the forecasting of the ocean state over, let's say, a week or 7 days, okay? That's the goal we want to realize. And we want to train this system end-to-end, meaning that we want to train and optimize the system to get the best possible forecast given the observation configuration we will consider. So now if we look at related work, so you all know the classic way to address this in an operational system, so based on data assimilation system. So this is, I don't know what, you may see my screen here. So basically using some data assimilation system, and you can get some initial condition of the ocean state using the assimilation system and combine using also a dynamical model, and then you can propagate the ocean state using the dynamical model, let's say your best the model you prefer. And we've seen recently emerging like new approaches based on AI for the same topic. But here, what's done basically that you can replace the dynamic model. So let's say your NEMO model, you can replace this by a deep learning model like GLONET or Shire. And if I'm not mistaken, you can, currently the state of the art is that you get very similar performance in terms of forecasting, in terms of, let's say, MSE metrics, for example, for different variables, but the deep learning-based forecasting is much cheaper in terms of the computational cost. So here again, what we want to address is not the second approach, okay? We don't want to train a deep learning emulator for ocean dynamics. We want directly to train a neural scheme mapping observation data, a GAPI observation data, directly to the ocean state in the future. And we expect that based on this, we can improve the performance because we won't be biased or by possibly some errors or the uncertainty in the initial condition you get from the data simulation system, which is used in, let's say, like GLONET forecasting. Okay, so in terms of organization of the work, so we have 3 work packages that refers to 3 specific objectives of a project. So one is really to work on the neural architecture we will develop. So we have some background using FortiVerNet that was mentioned by Jan. I won't detail it, but basically it's a class of architecture which relies on a variational data assimilation formulation. So we can bridge this to a classic data assimilation framework, at least formally, even if in the specific it's not exactly the same thing, but in method level that's the same. That would be one class of approach. We would also benchmark state-of-the-art architecture like a UNet that was mentioned by Julien in the previous talk. That very first objective. The second one is more to develop what we refer here as to machine learning ready workflows from the pre-processing of the data up to the evaluation of the different approaches. And so that we can automate as much as possible this whole process, and so that we can reproduce and for sure the whole process. That's very important, and that will be based on a very similar tool as the one mentioned by Julien in Anemoy. So we also combine here state-of-the-art tools used in the machine learning like PyTorch, Hydra, which are really a way to, again, standardize things and keep track on all the parameterization and configuration used. And the last one, which refers to work package 3 here, is all we deploy in terms of numerical experiments will be based on different benchmarks. What we refer as to a benchmark is a specific experiment for which you have data, specific evaluation metrics, and some baseline approaches you'd like to compare with. And for those baseline approaches, we'll consider both the operational system, forecasting system from Mercator, the GLOW forecast, and also the deep learning, state-of-the-art deep learning architecture I mentioned before, Chireux and GLONET. Okay, so here, so as all of the other projects, we just started like 4 months ago. So we are very much in a very early stage of the development of a project. So we started with sea surface height only configuration first, and then we'll move to a more complex configuration. Here we use a configuration on global scale, 1/4 of a degree resolution in space and daily resolution. The training configuration is that we train from the GRORIS ocean realities data set, meaning that we simulate the altimetry data. Okay, so it's a purely simulation-based training configuration, and then we apply the model trained on simulation data. We apply it to real data to assess the performance on real data. Yeah, there is an error here. I think we use a multi-year training data set, and we use 1 year for evaluation purposes, and currently is the year 2023. And we've been using for evaluation purposes the same benchmark in terms of metrics as the one developed by CLS and DATLAS for SSH mapping on global scale, so that we have some reference, and we adapted this for forecasting, and we, as mentioned before here, we use the GLOW forecast as a baseline. So here, that's the kind of metrics you get, so I won't spend too much time here, but you see we have different types of MSE-related metrics here for SSH. Here corresponding to different regimes of the ocean, corresponding to different regions, like coastal regions, or very high variability regions like the Gulf Stream. And on the top, you have the performance of the approach we applied, but based on the 40VAR-net. And the bottom one refers to the glow forecast. So if you compare, so sorry, I don't have my glasses here, so maybe a bit difficult for me to read, but you see that you have some differences, let's say 10 to 20% of possible improvement by the deep learning scheme. So we think here, so that's very preliminary. We need to, for sure, to consolidate this, but that's in line with what we observed for the mapping, the global SSH mapping experiment. So that seems consistent with this. Here you have, for the entire 2023 year, you have the map of the mean error average over the 1 year period. So, and you see that the more red, the more error you get. On the left for you, you have the deep learning scheme. On the right, the glow forecast. So you see more red on the right than on the left, if I make it short. So that's yeah, a good first step for us for a very first experiment. And just to mention here, so we have a forecast over 7 days. I won't show everything, but here it's just the evaluation of the performance for the first day without observation. Okay, and the summary. So yeah, I probably don't need to repeat the first 3 points. So we have a working version of our experiments with a Git repo, which is open source. There's a link here. I assume the slides will be shared. So if you'd like to access this, you can. And next steps are really to move to a multivariate configuration, both for the outputs and for the inputs. So what we address within the project is not to move up to a full 3D ocean state, but we plan to have a demonstration, let's say, for a reduced order representation of the ocean state with the sea surface variables, SSH, SST, and sea surface currents, and plus the mixed layer depth, and using as inputs different observation data sets, satellite observation derived for altimetry and sea surface temperature, plus Argo-related data for the mixed layer depth. That's it for me.
Thank you. So thank you to all the speakers of this session. So we now go to the very short Q&A session. So I've seen that there's already one question on the Slido for Dorothea. So the question, I don't know if you've seen it, the question is, how many parameters are planned to be calibrated? Are they a subset of the CICE model parameters?
So I only got the first question, is how many we have. I will start with 10, it's the one that we have already decided. Of course, during the runs, as we see how the model actually works in response to the optimization, we will add more, not only on CIs, but we have also considered snow and again interaction between ocean and atmosphere, like the drag for we both other component will be taken account. Yeah, most of them are actually part of the dynamics and thermodynamics part of size, but we will take into account also other things.
Okay, thank you. Are there other questions from the room? Apparently not. So we are just on time for the coffee break. And I have 2 very short announcements before going to the coffee break. So the first one concerns the lunchbox that some of you may have ordered. So you need to confirm that. So there will be a form to sign next to the coffee room. So please do that during this coffee break. And the second announcement is that we are going to have a group photo now. And we are asking you to go to the elephant. I guess you know where it is. It's very easy to find. And we will have the group photo around him. So please go there now.